Okay, so this is what we're going to talk about. We're going to look at some pre-introduction to Gaussian processes, and our focus will be on regression, the regression problem. We're going to look at parametric models and what we mean by parametric models. We're going to look at what we mean by non-parametric models, and then of course we're going to talk about the Gaussian processes. All right, so for a typical regression problem, we are given data, which is usually a tuple x and y. And we're interested in finding some function that describes the data. Okay? And in this case, we want to find that function with some level of uncertainty, okay, around whatever we try to predict or whatever values we try to, whatever point we try to estimate. Okay, so there are two possible families that we might want to, approaches that we might want to take. We might want to go using the parametric approach, okay, where you throw in a neural network or one of those deep learning methods. Or you can go the non-parametric and put in maybe a Gaussian process or do KNN. Okay, so to motivate the speech, let's assume we have data x, okay, and y. We can go the parametric approach where basically what we do is to pick some fixed number of parameters, okay, that tries to describe the data we're interested in. And then we can learn those parameters, okay, of our model, either doing maximum likelihood estimates, that is if, for example, we don't have a closed form solution to finding those parameters, or we can do map, which basically looks for learns and estimates the mode of the posterior distribution, okay, concatenated with a prior. We can also go the full Bayesian method, where we basically do some approximations to the posterior to describe the behavior of data. Okay, so as a motivation, let's assume we have this. By the way, these are just hand-drawn. Okay, so let's assume we have this data set. Okay, and we want to fit a line to this data set. Okay, a simple way to do this would be to fit what? A straight line, right? Now, if we fit a straight line to this data, it means we're going to have to, well, if you think of the equation of a straight line, mx plus c, so you have basically two parameters that you'll be tuning to get the perfect fit for this data. Okay? So, and that is what we have here. So basically, we're saying that to describe our model, we can use two parameters, okay, and fit a line to this model. And the parameters we're talking about, in this case, x1, well, theta 1 and theta 2. So we can either fit this model using MLE or map, okay? So basically, you're trying to evaluate what x1 will be for this data and what x2 will be for this data using any of those techniques, okay? Now, we may decide that what we want is not a fixed estimate of those parameters, but a distribution around the parameters. So intuitively, what that means is we have several lines, okay, that tries to describe the data. But the notion is we have just two parameters, okay? And if we do full Bayesian approach, what we're doing is we're trying to estimate a possible range of x1 and a possible range of x2, given the distribution of the lines that you see there. Okay? Now, we could decide, well, a line is not the best fit for this data. What we need is some sort of curve, okay? And in this case, we do a quadratic fit to the data, okay? Now, if we do a quadratic fit to this data, we're going to be estimating 3 parameters, okay? And the same way, we can do a full Bayesian approach to learning those parameters and get a distribution around the lines that will possibly fit that data. And we can do the same thing with a cubic approach. And basically what we mean is we are determining the number of parameters, okay, before we even train the model, basically. Now, the punchline here is, what if we don't want to decide the number of parameters we need to fit our model, okay, before we actually fit the model? Also, what if what we want is like that distribution you see, like a plausible function that describes that model, like a distribution of those functions that will describe the model that you see, okay? But we don't want it such a way that we are restricted to just maybe doing linear regression or cubic or whatever it is, okay? So we might want to be able to have some way of generating new data, okay, from our model. So basically, aka they call it generative models. So how do we do this? Okay. So let's see how we can motivate this with the non-parametric model. So when we say a model is non-parametric, it doesn't mean it doesn't have any. What we're trying to say is, well, what we're not saying is, how do I put it? It means there are parameters, but they are just not fixed. The number of parameters we have are not just fixed. They grow with the size of the data. So when we say non-parametric, it doesn't mean that there are no parameters at all in the network, in the model. It just means that we are not restricting our model complexity to either just 2 parameters, 3 parameters, or n number of parameters. And yeah, so how do we do this? Okay, cool. So what we want is a model whose parameter scales with the complexity and the data. Okay. We also want this model to possibly want a distribution of this functions that will try to describe that data that you just saw. So consequently, yeah, we want that distribution. So it sounds cool, right? Yeah. So how do we do it? Okay. So this is like a motivation for the Gaussian process. So imagine that you have these lines, this data, okay? So we can assume some notion of smoothness to say that the points that are closest to themselves are highly correlated, okay? So if you assume that the points evaluated at the points whose values are closer to each other are highly correlated, we can do some really nice trick, okay, to try to describe the entire function, okay? And that is the motivation behind what we're going to talk about in Gaussian process. So let's define a vector of functions, function values actually, okay? So what we're saying is the function evaluated at this point, this is its value, okay? So we collect these function values, it forms a vector, okay? And we assume that that vector points that are close in the value of evaluation are highly correlated. So that's the idea. So let's assume the notion of smoothness, okay? So if these 2 points are close to each other, we can sort of have some correlation defined by some matrix, okay, that tells us how correlated those 2 points are. Okay, in this case, so let's assume there are 2 variables here. So this is x1 and this is x2 on the row, and x1, x2 on the column. So what we're saying here is the variable x1 is highly correlated with the variable x2, because if you look at the value here, it's close to 1. Okay? All right? Of course, you expect diagonal to be the same, because the variable is basically saying is correlated to itself. Okay? And the same way, x2, okay, is highly correlated with x1, because obviously the value here is high. Okay? So if we have that, we can describe our GP. Okay? So what our GP tries to do is say that Gaussian processes assume that the neighboring points are correlated and the function values are distributed multivariate Gaussian. So what that means is those 2 values that you have there have some multivariate Gaussian distribution. Okay? Parameterized by a mu and a covariance sigma. Okay? And this is what is described here. Okay? So we describe a joint distribution between functions evaluated at fi and function evaluated at fi plus 1 to be multivariate Gaussian with the mean mu and covariance sigma k. Now, it will interest you to know that we can generalize to endpoints, to infinite number of points. So that's why you hear in some textbooks, they say Gaussian processes are infinite dimensional, okay? So for endpoints, we can basically collect all the functions evaluated at our index set X, and we assume a joint distribution over those function values, okay? And the parameters, of course, for our normal, multivariate normal is mu and covariance matrix K, okay? There are some additional note to this. For example, we need to find a way, okay, of generating this matrix, okay? And it goes a long way and in fact, this is one of the most important things in Gaussian processes. So what you're trying to say is, how are my variables correlated, okay? How do I define that correlation between my function values, okay? And yeah, of course, this variable must be positive definite, and they scale easily well to infinite dimensional spaces. So if you don't know what a multivariate Gaussian normal distribution is, this is what it looks like, okay? So this is a multivariate normal distribution. Usually, that covariance matrix you see defines the shape of this image, okay? And it is parameterized by the mu and, of course, the matrix that we saw. Now, there are really nice properties that come with this kind of distribution, okay? So this is a theorem. Now, if you have, suppose you have x, and you define x to be jointly Gaussian with that parameter, then the marginals is also a Gaussian, okay? So what that means is, okay, this variable is also a Gaussian, is also a normal distribution, parameterized by this mu, okay, and this covariance matrix, okay? In the same way, x2 is also a normal distribution, parameterized by this and this, okay? So that's what it means. And if you have this kind of distribution, the posterior of a Gaussian is also a Gaussian. That's what makes them cool. So we can say that if I want to evaluate the value at a particular point, given another point, okay, that is also a Gaussian distribution, okay? So if I want to find the probability of x1, if I have x2, this is also a Gaussian distribution, okay, whose parameters are this value here, and this is the definition, okay? So, and look at this clearly. This is going to inform how we try to get the closed form solution for our Gaussian posterior. We'll come to that when we see it. Okay? So like I said, if you come back here, one of the very important stuff we need to take in here is the fact that we have to find a way to encode how these variables correlate, okay, with this our covariance function, k. All right, so we can have, there are different choices of covariance function, okay, and this is one example, all right, of a covariance function for our Gaussian. So, well, like I said, remember we said it doesn't mean that Gaussian processes, when we say Gaussian non-parametric, it doesn't mean that they don't have parameters. It just means that the parameters scale as the data size grows. So if you look at this, this is basically how these 2 points, okay, correlate. And this is the parameter associated with these 2 points, okay? So if you have n point, obviously you expect this to grow, okay? And then these, our k in this case is, of course, the hyperparameters are this theta naught and this L, which is known as the length scale. And theta naught is known as the amplitude of our kernel. So there are different choices that you could pick, and This is very important because you can't just pick any covariant function, okay? So it's more or less like having some prior information of how you think the functions behave, okay? So if you think the function behaves in a Brownian motion kind of way, obviously you would like to pick this as your covariance function, okay? So if you think it behaves in this form, you might want to pick this exponential kernel function. And if you think it behaves this way, okay, you might want to pick that, all right? So basically what I'm trying to say is you need to have a prior knowledge of how you think your functions will behave, and that will guide the selection of your covariance function. Yeah. You look at the data. Okay? We'll get to that. All right, so I just mentioned something, right? I said you need to have a prior knowledge of how this function, your data behave via covariance function. And then once you have that, you can get a posterior by doing simple Bayesian method, okay? Where you multiply the likelihood of the data times that prior knowledge that you have divided by the margin over the entire data space, okay? And this is what is shown here, okay? So what we're saying is, if I define if I have some prior information encoded in my covariance function, that gives me this, okay? And I have to also determine how likelihood I think my data, the likelihood function for my data, okay? If I have that divided by the probability of seeing the data itself, that gives me the posterior, okay? And this is what is typically known as Bayesian method, okay? And this is how we calculate the posterior for our Gaussian, okay? So we basically have, it's like saying, well, before I see the data, how do I think, okay, these functions will behave, okay? So once I have that, okay, and after I've seen the data, okay, how does it now behave? That's basically what you're doing, okay? So, yeah, so this is, in some iterative process, this could be recursive, basically, okay? Well, we're not going to talk about that, but I'm just trying to make you understand. And then you can also have a closed form solution for this, which we're going to see in a moment. Okay, so this value represents the prior information, the prior knowledge you have about your functions. Okay, this is supposed to be is our likelihood of the data given the function, okay? All right, and this is the posterior, okay, of our function after we have seen the data. Now, so what do we mean by all this, okay? This is typical Bayes rule, okay? Where we say, well, the posterior, this term, okay, is the multiplication of the likelihood function plus our prior knowledge about what we think the parameters are divided by d. So then again, how do we define this likelihood function? Because obviously we need it, okay? If we're going to do Bayesian, we need this term multiplied by our prior information, and then to get the posterior, we'll do that multiplication. So the likelihood is your model of how the data was generated. All right? Okay, so to answer your question, yeah, so all probability modeling starts with a preliminary analysis of and visualization or inspection of your data as a standard. Okay, and this is called, in statistics, it's called the exploratory data analysis. Okay, but it doesn't take away the fact that it violates the spirit of posterior specification unless the prior is engineered to look exactly like what you want to see in the data. So what we're trying to say is this: if you don't know, if you don't have any prior knowledge, okay, about your function behavior, you might as well just use some uniform distribution. Okay, because what you're interested in, what you're interested at is finding that posterior, what happens after you have seen the data, because that function will be updated anyway, okay? But if you have prior knowledge, okay, of the distribution of your data, then it helps better in achieving the posterior distribution. Okay? Now, so let's look at predictions. So we have data D, and we want to predict the value evaluated, value y star, okay, given some test point x star. Okay? Now we can simply put up our model, okay, to be such that, okay, if we assume some random noise, okay, we can say our y is equal to some function evaluated, yn is some function evaluated at that point plus an error term, okay? And if you assume the error terms are, the error is a normal distribution, then we can easily get a likelihood that is Gaussian, especially if you assume that each point is independent and identically distributed. Okay? Once we have that and we get our posterior, we can easily do prediction theoretically doing this. Okay? If this is not so intuitive, just hold on, you'll see what I'm talking about. Okay? Now, if we assume a Gaussian noise, okay, defined by this model, and we say that our E is normally distributed with zero mean and some sigma square, and we assume that each of the y's are independent and identically distributed, then we can just basically do change of variable, basically, okay? And we'll see that clearly that our likelihood, that likelihood function that you see, I talked about here, okay, is Gaussian, okay? And if this is Gaussian, and we assume a Gaussian prior, if you multiply a Gaussian likelihood and a Gaussian prior, you also get a Gaussian distribution. And this is what motivates a closed-form solution that you're going to see here, okay? All right? So remember, this is our posterior, okay? So if you assume that our posterior is approximately equal to this term, okay? Excluding this anyway, all right? And this is a Gaussian, and this is also a Gaussian. Then if you multiply two Gaussian, you get a Gaussian, okay? All right? And it goes from here, okay? It says if our likelihood is a Gaussian and the prior is a Gaussian, then the posterior is a Gaussian defined by this formula, okay? So basically what I'm just trying to do is, if I want to evaluate the points, if I want to get prediction, I'll basically have that notion in my head that my posterior is a Gaussian, okay? And just do substitution, all right? And this is what I have here, okay? So our posterior is a Gaussian, okay? Parameterized by this mu and, of course, this covariance function. And it's identical, okay, to this line, okay? So if you look closely, of course, they are using x1, x2. In our case, we are assuming that the function evaluated at each point, f, okay, is jointly Gaussian. So I will just replace all this with f, basically, okay? And then I have this. So what am I saying in essence? Okay? If I want to make predictions, all right, and I want to do Gaussian process predictions, okay, regression, for example, and I assume that my likelihood function is also Gaussian, okay, I can simply get the posterior distribution just by applying this formula, okay? And so what are these terms? This, okay, x star is defined by k star, okay? And k star is actually the covariance matrix between your training sets, okay, and your test sets, okay? Ky is the covariance matrix plus noise times the identity of that matrix, okay? And of course, y is all your y values that you have here, okay? Similarly, this is equal to the covariance between the test sets, okay, minus, of course, this term, inverse, times K star. And this is the definition, detailed definition of that, okay? So if you, when you have the time, you can quickly look at this, okay, and see how it relates with this, okay? Basically substituting for every x values you see there, because we are looking at distribution over function evaluated at x. So it's a multivariate distribution over those function points, okay? All right, so what I'm saying in essence, if I have data, okay, all right, x and y, okay, I can basically get a vector, all right, of all the y points, and assume that is jointly Gaussian, okay, and then I can calculate the covariance matrix, okay, x star, all right, which is defined by this, all right, and then for the, of course this is a function of the test point anyway. So if you look at it, this is the covariance matrix between the value, the training set and the test set, and this is just the covariance matrix, okay, plus some noise, and this are the values of those y's. And if it's still very fuzzy, there's a code that we wrote in Python that just gives those steps, okay? So you can actually hard code it right there and see how it behaves. Okay, so this is the definition of that. And this gives you a closed form solution, okay, by the way. All right, so it means if I have x and I have y, I can form some covariant matrix, do some matrix inversion, and I get a prediction, okay? I could do that differently by maybe MLE, which he will talk about. So, now, like I said, when we talk about Gaussian processes, it doesn't really mean that they don't have parameters, okay? But what are those parameters? Now, which I showed you that these are some of the parameters that you could have. Okay? Yeah, so this is for this particular kernel, these are the parameters. So you have two choices, actually. Okay, you could actually fix those parameters, okay, and get a closed form solution using this formula, okay, or you can learn the parameters from data via optimization. So this is what I'm trying to say here. So how do we choose the hyperparameters for a Gaussian? So we can actually do that using optimization to find the hyperparameters that fits well with your data, okay, or you just assume fixed hyperparameters and then you go, okay, and do your predictions. Now, remember, the reason why we could do this closed form solution is because we are assuming that our likelihood function is Gaussian. It is this, okay? So that if you multiply the two, you get a Gaussian distribution, all right? But if it is non-Gaussian, of course, if you multiply that, you don't get a Gaussian distribution, so this doesn't apply, okay? So you have to resort to other means of finding the posterior distribution. And some methods that people employ is sampling and some analytical methods like expectation propagations and the rest, which we're not going to talk about. Okay? Yeah.
How do you do the optimization of the hyperparameter?
Okay, well, you want to answer that?
And you use what you're optimizing is the marginal likelihood. So that's the likelihood marginalizing out all the parameters. Well, in this case, the latent function, the GP. And then you use the LVGF. Sorry, if I get the order of those letters wrong. Please do. Or you can use other kinds of quadrature approaches. Basically, any cross optimization. LVGF is common.
Okay.
Can I add something really quickly?
Yeah.
If you really care about it, then you can also do something maybe the distribution of hyperparameters as well. You might have you might not be very confident about exactly what values mean, so you can maybe ensemble methods just to add more.
So, ensemble methods, right? Okay. Yeah.
So essentially doing the exact same thing, not looking for a point estimate for
Yeah.
hyperparameters, but
Yeah.
considering that also have a distribution.
Yeah, yeah. Okay, so why should we use Gaussian processes? Okay, very good for time series data, as you would see. Okay, they directly capture model uncertainty, especially when that is very important in your predictions. They work very well with not so large data, sizable data, and that's because it's easy when you have hardware where you can actually fit those the matrices and do matrix inversion, then it's fine. Okay, and they have the ability to encode prior information, like we just talked about, and they handle model complexity and scalability very well. So why they're not so great? Okay, for example, I said you're not so great for large data sets because, well, think about it. If you use all your data, if you have very large data set and you use all the samples, you're going to end up having very large matrices, which you're going to invert. Okay, there are ways to tackle this anyway. Okay, for example, if it's very large and the inverting those large matrices is so complex, you can actually parallelize the process. Okay, or you can actually represent those large matrices with a smaller one, sparse GPs. That's what they're called. Okay, and still achieve do some approximations of those large matrices to work. And they may not be your one go-to option for classification. Probably he will talk better about that. Okay, that's what I think. That's my opinion anyway. There are professionals here who will probably explain better, I guess, or say that's not true. All right. So, like I said, there's a notebook, okay, where we basically just walk through coding this. Okay? So you have the data, all right? And you have some training points, and you try to evaluate some distribution over this point. So any question before I show you the notebook?
Can I just, I'm not sure, but is there a term in the variance function? It doesn't matter.
What?
Like, isn't there a case style transpose before, in the previous slide, it doesn't matter.
Which one?
People are implementing this.
Okay, this one?
Yeah, is there a case style transpose before the bottom term?
The bottom term?
After the minus sign.
Yeah, I will look it up.
It doesn't matter, but just if people are actually writing it down.
Yeah.
Doesn't matter.
Yeah, I could correct it. I'll look it up anyway.
I just want to highlight it if people actually go to program it.
Yeah, I think there's one more term in this. Yeah. Yeah. So yeah, I'll look this up and make some corrections. Okay. So any questions?
Does it work also for discrete data? You don't show the regression page.
Yeah. Does it work for discrete data?
Or is that the time?
So I'll go into a little bit about how you can use it for classification problems.
Yeah.
Some kind of discrete data. Yes.
Yeah.
So the short answer is yes. But where the GP is a surrogate for some underlying function that you then pass through another function which takes you from continuous space
To discrete space. Yeah.
like a signal.
Logics.
But in terms of how well they do, I mean that's down to like
To
how
debate.
well any model does. But, it can be good, it might not be.
So I'll just briefly walk through the notebook. And then, of course, if you want some additional resources, you can check out this book. It's actually very good. Okay. You can check out Neil Lawrence's notes, inverse probability. You can check out Lehel's notes and some other lecture and video notes. So, like I said, any questions? Cool. All right, so this is the notebook. It's quite really short. Okay. First, we import NumPy and PyPlot just to plot what we have, and then this basically just sets the size of our plot, and this is our kernel function. Okay. So this is where I make those matrices. Okay. Now, like I said, I would like to visualize what this kernel looks like. So I basically generated 50 points. Okay. Our parameter for this function is this. I set it to 0.1, and we get index set x to range from -5 to 5, and there are 50 of that. And then I make just the kernel function, the covariance matrix, based on the kernel function that I display. And then, yeah, there's this point called where this gives me the variance, right? So if you're going to get the standard deviation, you probably take the square root of the variance. And there's this function called the Cholesky decomposition. Is in linear algebra. Basically, what it does is just to take the square root of the variance, which is in this case in matrix form. Okay, so this gives me L, which is my standard deviation, and then every programming language gives you some way of generating standard normal distribution. So what I did was generate the standard normal distribution, okay, multiply it with the standard deviation, okay, and if I assume 0 mean, I can plot what it looks like. And this is what I have, okay? So this is what I'm assuming my function will look like before I even see the data. This is my prior information, okay? Now, if I want to make predictions, let's say I have points, this is my x data, and I have, these are my training set, x train and y train. And this y train is actually some cosine function, 2.5 times some, just some function, you can play with that, okay? And I'm assuming that, of course, if you've ever seen a sine or cosine function, it basically looks like some wiggly stuff like this, okay? So I have that prior information that I'm going to get some posterior that looks like this, okay? So this is my training sets, x train and y train, and these are the points for which I want to evaluate their values, okay? So what I do is to make the first kernel function k, okay, which is how my training sets basically correlate, and then I make and add some. This is my ky. If you look at the notes, okay, which is k plus this noise parameter times the identity, and ks is actually the covariance between my training set and my test sets. And then, yes, so here I evaluate this mu. If you look at the slide, the mu star, this is it, okay? And if you also look at the slide, this is like applying that same formula for the covariance matrix, okay? But there's one slight trick here. If you notice, I do a lin solve between k and k star. So basically, I'm assuming that if I have a situation where my matrix is not invertible, it's not full rank, okay, I might want to have some approximate solution to my variables. Otherwise, I could have just done that matrix inverse multiplied by y, okay? And that gives me my sigma, all right? Now, in order to visualize it, to see the level of some uncertainty, I take the standard deviation of my sigma, and then just got the diagonal element, okay? And in the same way as this, all right, I plot it to try to see what my posterior distribution will look like, okay, given my test data. Okay, so I draw the standard normal, okay, reparameterize it with the mu and the sigma, and I make random draws, okay, from that distribution. So if I do that, I get this, okay? So what does this tell me? This is my prior knowledge, okay, of how I think my functions behave, okay? Now this is how my function behave after I have seen the data. Okay? If you notice that the gray area is the uncertainty in your prediction, and at the points that are already okay, so if you notice, you see that these functions, they basically wrap around, okay, these points. All right, and these are the points that points closest to this point, I'm more confident about them, okay, as opposed to points that are far away from these points. So this gives me some way of doing proper interpolation, okay, and having some form of uncertainty in my prediction. So like I said, this is just to give you an intuition on the slides, okay, the equations you see on the slides, and you can, if you are okay with walking through the codes, okay, and try to compare what we have in the slides, this will help you better, okay? But if you're going to do GPs in production environment, you might not want to be coding this, okay? You'll probably want to be using GPPy and some other libraries, which Michael will talk about. So any other question? Any questions?
When you have the posterior, what is your evaluation?
Well, in what sense? Like
okay, you have the prediction.
yeah, so this is my prediction after. Okay.
How do you evaluate whether it's the metric, whether it's to what extent is it predicting?
Yeah, that's why these error bars are there. So what it's saying is, if remember I'm trying to predict for X star, okay, and there are points from -5 to 5. So what you're saying is, I have a lot of confidence when I'm predicting the value. This is actually the value, the prediction of this point, and this is its value, okay? And I have a lot of confidence here. If you notice, the variance is shrunk a little, so I have more confidence here predicting this point. Same also, more confidence predicting this point, okay? As opposed to predicting the points maybe somewhere in between, or even somewhere here, yeah.
The red dashed line, if you're just computing square root, for example.
Yeah. So, any other question? So, thank you very much. Yeah? Okay.
Half an hour.
Got it.
No, okay.
Oh, okay, cool.
Just looped it around there.
I almost forgot that I had it on.
Fantastic. Good stuff. Sorry. Can I get you to wear this?
No, right on.
Yeah, it's worked really easily. Sweet. Nice bit of hassle.
All good. I just want to make sure I get the thing clipped on.
Yeah, it's a bit flimsy.
All right.
Stick it in a pocket, I guess.
Yeah, great. Okay, good. Working.